and so on and so on. But of course also shaft and fluidized bed reactors where we do solid state reduction or even plasma support solid state reduction. Then electric arc furnaces, of course, where we do not just melt the iron sponge, but can also use them for plasma state smelting reduction processes. And of course, electrolysis, which we also do in our institute, but this is not covered by the talk today. So as I said, in my specific group, in my institute, we work with hydrogen-based reduction, with electrons directly, and with plasma-based reduction. Now let me delve a little bit deeper into the direct reduction, which is a solid state oxide exposure, and we use as a reductant here hydrogen in H2 form. So the principle is shown in this little animation, which I took from the homepage of the company Midrex, and that is well known to all of you. So you have a counter-stream shaft reactor, which is currently fed by steam reforming, of course, but you can do that also, as you know, with pure hot hydrogen, and the redox product would then be water. And the overall schematical principle of what you do with that reduction product, namely the so-called porous iron sponge, is shown here. You feed it maybe together with scrap into an electric arc furnace and bring it then to the downstream level metallurgy. And the balance is that you can operate that with 70 to 80% less CO2 emissions when you use hydrogen, but we all know that is a bit of a pony farm comparison when we don't have a fair estimate what the CO2 costs are from the grid for making the hydrogen in the first place. So the second aspect that we have to keep in mind, that's why we have to take this very broad research approach across different technologies in the next decades, is that this amount of sustainably produced hydrogen is simply not available, where you would need for the 1.9 billion tons of steel produced per year, something like 250 to 270 million tons of hydrogen every year, and that does simply not exist, as you know. That's why we also look a little bit into sustainably produced ammonia, where there are novel plasma-based ammonia production methods that are less CO2 intense than the classical Haber-Bosch process, to use something like ammonia also as an alternative carrier, because that is already a 180 million ton global market. So when we go a little bit deeper into the physics, we look at the reduction kinetics here for a direct reduction process that is taking place under pure hydrogen at 700 degrees centigrade. And that is, of course, by solid state direct reduction standards, a rather moderate temperature, but we do that by purpose to make things nicely observable. So when you take a look at the right-hand side diagram, then you can see that, that you plot here the reduction rate as a function of the reduction degree, as you see here. And when we start with the trigonal hematite, Fe2O3, you can appreciate that the first step in the reduction is very fast, going into the cubic inverse spinel magnetite very rapidly. But when you are then in the cubic magnetite and transform further to FeO, which is likewise cubic, and they are sharing the same oxygen sublattice, then you lose reaction rate. And when the wüstite, which is gradually forming here out of the magnetite, in part at this temperature even out of the hematite, as we can find, you lose nearly 1 order of magnitude in reduction rate before you finally arrive at alpha iron. So that is kind of a challenge. We also look at that from an atomistic perspective. I show here a typical slab. We do that in a collaboration with Kei-Jung Lee, where we try to look at these processes from an atomistic perspective. We use a published reactive force field moment at the moment, moment model, but that is still not very good when it comes to the reproduction of the actual crystal structures of the alpha iron, but at the moment we use this model only for looking at the reduction kinetics in the first atomic layers. We have meanwhile developed massively improved machine-learned bond order potential that can also take over reactive force field roles. That means you have a near DFT quality reproduction of the solid side and of the reaction rates when it comes to direct reduction. So just for you to know that we work intensely also on the atomic scale understanding of these processes. When we take a look, and I hope you can see the movies okay, when you take a look at that interface of the final state of the Fe2O3 plus the H2, as you can see here, then we start to understand how the actual first water molecules are formed and how the diffusion, how the transport processes in the first layers occur. Here you can see on the left-hand side the distribution of the oxygen after 680 picoseconds from this type of simulation. On the right-hand side, you can see how the hydrogen is entering into the solid and sweeping the material. So the individual production steps of some of the water molecules are picked here and highlighted just as an example to show you what kind of insights we expect from this type of research. You can see here after the different time steps that you have many intermediate steps, how the water molecules are formed and then are finally evaporated into the steam. And here's another process where you see also an intermediate OH type of step, which is still bounded to certain motifs that reconstruct at the surface, and then off it takes, as you can see here. So these are just very elementary atomistic insights that we try together to understand these things better. In a little, again, reactive force field MD simulation, you can also see that when you have formed the first tiny iron layer, the surface, as you can see here on the right-hand side, these silver-colored atoms are the iron that forms after a few layer reduction step at the surface, act as a core shell structure. And that means you directly after the first iron shell has formed, and you must bring the oxygen outbound through that already reduced iron, you have a change in the overall kinetics. I found that quite interesting to even see that very quickly here at the atomic scale. And some of that, when I switch now back to experiment, you see also in this little environmental electron microscopy movie that has been taken in a scanning electron microscope where the entire column is flooded by hydrogen. That experiment was done by my colleague, Professor Mark Willinger. And you can see here that you have that rough appearing surface, which is a single crystal wüstite material. And when you expose it now to hydrogen in the electron microscope, and you let that movie run, maybe run it again, you see that the material is overgrown by relatively, flat appearing iron layer, as you can see here. That means the take-home message from this very slide is that you produce very quickly, of course, core shell structures. And the oxygen must be transported outbound through these relatively dense iron layers. As you can see here, when I highlight that a little bit better at higher magnification, now in a cross section, then you can see that here are areas with patches where you have remaining iron oxide wüstite at 700 degrees centigrade, again by purpose at a relatively low temperature. But then you can see that the iron layer forms rather densely around that wüstite. And you need to bring out that oxygen, and that must then diffuse through that relatively dense iron layer. So that makes things relatively sluggish to proceed. And that is just the same thing at a higher resolution in the microscope. And you also see, of course, all that porosity that is evolving here, which is, of course, due to the mass loss. So every oxygen every oxygen atom that is left produces an anion vacancy. The vacancies are collapsing. We assume mainly at these proceeding interfaces between the metal and the wüstite oxides, and they coalesce and form then a complex porosity pattern. But we will get back to these porosity patterns as you see here. So that's about where we stand with understanding these core shell structures. And when we jump back into this atomistic picture that I have tried to share before, then we can render this schematic by showing the wüstite on the left-hand side, the interface to the iron layer above it, and the necessity to have the oxygen atoms here shown, oxygen 2- anions, shown here in blue, stripping off the 2 electrons so that as an oxygen atom it can diffuse outbound to form the water or the next nearest surface. And the next nearest surface is not necessarily the free percolating surface, but it can be also one of these inner pores that I've shown to you before. Because the oxygen is not very smart. The oxygen is just following a gradient in the local chemical potential that points at any free surface, be it an inner or an outer one. Now, when we take a moment to look a bit more at the mesoscopic scale, here by the aid of EBSD, so electron backscatter diffraction analysis, we can see that when we do now these experiments on commercial pellets, not on single crystals like we usually do, then you can see here the as provided sinter structure from the polycrystalline pellets with the sinter porosity, where you start, as you know, with 22 to 26% of sinter porosity for the MEDEX operation at least. And then you have the black lines indicating grain boundaries in the hematite. And then you see this nice polycrystalline structure of the initial hematite here in this blue color. Now, when we go at 700, a little bit ahead towards 1 minute reaction exposure towards pure hydrogen, again, the atmosphere is pure hydrogen, you see of magnetite here in the yellow color. And that is forming more in an Avrami type of nucleation growth process. These two crystal structures are not commensurate, they are incoherent, and you have correspondingly incoherent interfaces that form with many additional new grain boundaries. And the nucleation, not surprisingly, as we learned from the atomistic simulation, start, of course, at the available free surface. The hydrogen itself, by the way, is not a bottleneck because it kinetically sweeps the material very, very fast. That means before any process in the interior arrives, the hydrogen is already there. So the bottleneck is the oxygen transport, not the hydrogen transport, as far as we can tell. Now, when we go towards 5 minutes, we see the decomposition of the magnetite into magnetite and wüstite, as you see here. That is a very, very interesting phase transformation, as I will also show on the next slide, because it's not a classical nucleation growth process, but it looks like a reshuffling of the iron cations in that lattice, which is, as I said before, for magnetite and wüstite, the same when it comes to the O2- positions. So that's a very interesting type of phase transformation. And remember, that's that part of the transformation where things also get very, very slow. And then you arrive finally, of course, at the formation of the alpha iron at 700. Sometimes you see in papers also very high temperatures in direct reduction, which I think is in part a bit questionable because you don't want to arrive in gamma iron because then the diffusion coefficients will be very low. So one must, for a reactor scale, where we also do collaborations with people who do the complete gas dynamics simulations for complete reactors, you must keep in mind the rather complex temperature distribution inside of these furnaces. You also learn from this diagram a rather heterogeneous progress of the reduction. That means we still find patches of magnetite and wüstite. So there's not always just a very linear progress of these phase transformation. And of course, you see the acquired porosity, the evolving porosity due to the massive loss of the oxygen everywhere. So you can appreciate the formation of an iron sponge, up to 45–48% of final porosity altogether. I'll come back to this. Here you see one little patch of information on which we work quite intensely at the moment. That is a magnetite to wüstite phase transformation that I've showed you before. We sit here in a single crystal, as you can tell from this IPF figure. IPF stands for inverse pole figure imaging from the phase discrepant EBSD analysis that shows you we live here in a single crystalline wüstite entity. But when you go to the phase discriminating map, where you account for both the martensite, the magnetite and wüstite separately, and you must take many Kikuchi lines for this into account to tell the two from each other, otherwise in EBSD everything looks the same. You can see that there's a very cubic edge-on-edge 100 interface structure evolving with this decomposition into the two phases. And from the kernel average misorientation on the right-hand side, you can also see that we have a build-up of GNDs. So GNDs stands for geometrically necessary dislocations, and kernel average misorientation refers to the curvature that you get as a metric out of the EBSD measurements. And from the kernel average, from the local lattice curvature, if you want, you can calculate the GND content. These geometrically necessary dislocations are interesting and important in the context of direct reduction because the diffusion along the dislocations that you can see here is much, much faster than through the bulk material, of course. But the microstructure is much more complicated, of course. When you look into these partially reduced pellets, like you see here, and you can find the details here in this ACTA paper that I'm showing you at the bottom of the slide, you can see that you have a complex interplay of the phase transformation, of the porosity, and so on. And I only show two patches here. You can see many, many more details, of course. And you can also see that you even have delamination, fracture, and so on. That means, in part, you also create new surfaces. That is quite important to understand. And when you go now to the pellet scale, to the polycrystalline sintered pellet scale, here you can see that they have an average diameter of 1.1 centimeter. And take out one of these now in a polycrystalline state in the S-sintered condition, then you can do the same type of microstructure analysis that I have shown to you before. And you can do that very systematically over large scales with different step sizes to get statistics of the grain sizes, of the porosity, of the connectivity of the porosity. That is very important because otherwise you then don't get the water stream out as a redox product, and the interfaces and even the dislocation content from all these structures. And this is all research that we in part keep on doing. And when you cut out such a patch as you see here, we also wanted to do a local boundary condition treatment in terms of theory. And this is now mesoscopic, a mean field theory, where we cast this phase transformation during the last step, where you transform the wüstite into the alpha iron into a generalized form of the Ginzburg-Landau equation, which is nowadays also sometimes called phase field theory. And we use here or bring together two variants of this theory. One is the so-called Kahn-Hilliard model, which is a diffusive phase field model where you conserve the quantities. That means the diffusing chemical species are conserved, and you must describe the corresponding energy landscape between the wüstite and the alpha iron by a generalized Landau energy potential form that you can fit from thermocalc data. And secondly, we combine that with an Allen-Kahn theory. And Allen-Kahn theory is a form of the Ginzburg-Landau equation for non-conserved variables that enables you to describe the phase transformation. That means, and then when you solve this in the form as you can see here, you can see the intrusion of the hydrogen, the formation of the water because you take in these balancing chemical redox equations, and you can particularly see and locally predict how the formation of the iron here in terms of yellow color proceeds also in these heterogeneous pellets. So this is just to show you, maybe I run it one more time. Here you can just see that we also use these generalized phase field theories to do a pellet scale simulation of the reduction. You can use the same thing, of course, for a blast furnace or for other reactor types. This is just general theory development that we can use in that context, and it's very insightful to understand how kinetics is, or how maybe the role of gank elements would come about, and so on. Now, when I push that type of theory work a little bit further, and I do that with two fine colleagues here, Jabamir Moody and Yambal, then you take such a pellet piece, you render it digital to differentiate the wüstheit phase from the pore structure, because through the pore structure you have, of course, different flows of the reactants, the hydrogen and the redox product water. And then you do these simulations now with a third ingredient besides the Kahn-Hilliard and the Allen-Kahn type of contributions, namely with mechanics. And you start here in a relatively simple form by inserting the mechanical penalty into the total energy form. And that is, you take for each oxygen atom that you take out of the wüstheit, you translate it to a displacement, of course. A displacement gradient brings you then the first linear form of the displacement gradient tensor, which we call an elastic strain. And then you put that elastic strain into the Hooke's law, and then you have an equivalent for Mises stress, for instance. That means during the progress of that reduction, you can also track how the stresses are building up, because the stresses are much, much higher during such redox processes due to the mass loss, due to the oxygen loss, compared to the typical stresses we know in metallurgical phase transformations, which are comparably really, really tiny. Even in martensitic transformations, the stresses are comparably small. So in these redox phase transformations, the stresses are much, much higher. You can see that here you ramp up to something like 5.5 gigapascal stress. These are very, very high numbers. We, of course, also immediately see that this number must be nonsense, because the oxide, the wüstheit oxide, cannot bear a stress of 5.5 gigapascal. Otherwise, it would be great construction material, but it's not. That means you must also appreciate that the elastic stresses are kept due to fracture or due to plasticity. So we also build corresponding phase field models, as you show here in that patch, and details again are shown here in this ACTA paper that you are welcome to read. That we build, of course, in a simple J2, so isotropic plasticity law, in where we consider both the elastic and the plastic relaxation of the material. Quite important, not just to show, look, we arrive then at realistic stresses of 500 megapascal that can build up in the wüstheit before you get plastic, but we also then have information from the simulation about the buildup of the carriers of this inelastic deformation, namely of the dislocation content. And the dislocation content, again, is very important to know to understand transport and fracture phenomena. So this is just to share you a little bit that we also try to capture these redox processes in the form of mean field models that we can use in the conjecture or in the context of very different reactor types. Otherwise, we have no real micro-macro coupling when it comes to the design of the reactor, or to the use of new reductant feedstock, of mixed feedstocks, or of different types of oxidic feedstock material. Now next, I talk a little bit about the porosity buildup. As I already told you, from the pellet sintering, you have something around 25, 28, 27% sintering porosity. And that ramps up towards something like 45 and beyond due to the oxygen loss and the associated porosity formation during the reduction. Again, this applies for 700 degrees centigrade. And when you break these hematite single crystals open after some of that porosity buildup, you can see a very fine and very complex pore structure in the inside, as you see here. So you have some of the very coarse and interconnected pores, but you have also this moon type surface in the fracture surface from the many tiny porosity features that are building up during the reduction. And what is very, very important to understand what the connectivities of these pores are, because again, this is important for the gas transport outbound of the water product. So we studied that also down, as you see in these tomographic movies, down to the microscopic and nanoscopic scale to understand from 3D microscopy, tomography, the details of this porosity build-up. And again, we subjected then to the same type of models that I have introduced a couple of slides before, where we apply such a scenario of porosity being connected versus porosity that is not being percolating in that phase field model. And you can see that while you cool the material down and capture the redox product water in some of these closed pores as opposed to these percolating pores, you see that you get a reoxidation of some of these pores when they are not connected. While the pores that are open here also in that simulation box can transport the water outbound. So let me run that movie again. And that shows you that we need to be aware of the understanding of the porosity, not just for fracture, but also for mass transport and for reoxidation when you capture the water in them of the already reduced iron. And that is shown here from an experimental investigation that was done by my colleague Red Zhou in an electron microscope, where you can see in red color, this is now colored not by EBSD, but it's done by diffraction in the transmission electron microscope, an already reduced patch of iron from hydrogen-based direct reduction, and the inside capturing the water inside, and the inside that was reoxidized in the inner surface, as you see here. And that means when you calculate and translate that to the corresponding enormous surface that you have in these pellets with their porosity structure, that means you lose a few percent of this material altogether. So that is kind of shown here in that overview diagram, if you wish, schematically. Now we also went down to the atomic scale to study the direct reduction. What we did here is that you see a patch of wüstite, single crystalline wüstite, and that was prepared in an FIP, and you see it being exposed to deuterium, so to heavy hydrogen, and to study the direct reduction direct at the atomic scale in the atom probe. And you must do that with deuterium, otherwise you always have hydrogen contamination, which is not so indicative. So you see here on the left-hand side the iron oxide, and after 5 seconds in that setup, you see that the outbound material is already now pure iron, and the inside is the remaining oxide, as you can see here. So we interrupted stepwise this type of process. And you can see on this overview picture that was run by Ayman El-Zoka, who is now in Imperial College, and by Seo Kim, who is now a professor back in Korea. When they run this experiment, you can not only see how the iron is forming around this iron oxide, but you also can see where the water, in this case the heavy water, deuterium water, is being formed. So again, that is the same context. I show maybe the movie to show it a bit better. The same context where you can appreciate and realize the interplay of the redox processes and the corresponding formation of the water in these processes. So and the single points that you can see are single atoms and ions. So we do these things also at the atomic scale. What we, for instance, also learn from that is shown here, namely that it is not just the emergence of the first anion vacancy coagulation, but it is also their relationship to further gangue element relevance, such as sodium and potassium, which are of course well known to attract water. So there is an interplay between the gangue chemistry, the porosity formation, and the accumulation of water. Now, I have many more such data, but I go now to a slightly different topic towards showing you a little bit about what we do with other hydrogen carriers like ammonia. Ammonia has 3 hydrogen atoms, as you all know. And the idea is through a splitter where you take the hydrogen out of the ammonia, you get hydrogen in your reactor, and the hydrogen is doing the same type of direct reduction that we have seen before. And that is what we studied in a series of papers now. One paper is in the press. And of course, as we all know, is that like for the production of hydrogen, it depends on what the grid electricity is, what CO2 and energy footprint you have to make the ammonia in the first place. Now, in this paper that you see here and are welcome to read, it should be open access paper, we learned that when you directly omit the use of an ammonia splitter and let the ammonia directly intrude into the reactor, you get, due to the catalytic effect of the first iron that's being formed, an autocatalytic, so self-accelerating process of decomposing the ammonia into nitrogen hydrogen. That happens typically at 450, 470 degrees centigrade. But when you have iron as a catalyst present, obviously in that reactor, this reaction temperature of ammonia splitting drops to about 350 degrees centigrade. That's quite interesting. So you have already at 350 degrees centigrade free hydrogen from the ammonia available in your reactor without using any splitter. And the kinetics, the reduction kinetics, is the same as using hydrogen alone, as you can appreciate from this comparison. So this is all done, of course, by TGA measurements, by thermal gravimetry. When you take an EBSD picture of such an ammonia-based direct reduction process, again, where the ammonia has not been splitted but has directly been charged into the direct reduction reactor, you can see here the grain size distribution of the reduced material in the direct reduction. But when you look into the EDS, you can also see from the chemical mapping that you seem to have a lot of nitrogen in the material also. And when you study that in more detail by, again, phase discriminating EBSD, you can see that we form a lot of iron nitrides, up to 40%. And this is also something we study in high detail now in the atom probe. And I don't walk you through all the details of this nitride physics, but it's extremely interesting to see. However, that means we wanted pure iron, and what we got is a duplex material of iron and nitrides. But when you put that into the electric arc furnace to melt your material, this mixed iron sponge, the vapor pressure of the nitrogen leads to the complete removal of nitrogen from the melt, so that you are left with pure iron also. So that's only an intermediate product that you see. So in other words, when using ammonia, yes, you can make pure iron. And now I switch gears, but only with one very brief introduction due to time limits, that we do a lot in the field of hydrogen plasma-based smelting reduction. And that is shown here. You charge up to 10% of hydrogen into a mixed argon hydrogen plasma state. And then you have a progress in the formation of the iron that is formed at the interface to the reacting plasma in that liquid state, and the hematite has only 50 Kelvin higher melting point than pure iron itself. And that sinks down the freshly formed metal due to its high mass density compared to that of the liquid, ionic liquid, sinks down very quickly, and you get, as you see here, pure iron from plasma smelting. And we go through all the same painstaking type of detailed microstructure, chemistry, and kinetic analysis that I've shown to you before. But I show you only a brief glimpse here, a brief snapshot in the interest of time. So we use this as a totally different technique to make green steel with electric arc furnaces. And a third direction that I'm calling tertiary production, tertiary synthesis, means we have also a lot of waste streams in so-called circular economies, and that waste stream can be a valuable source of feedstock also, as I briefly mentioned in the beginning. Now, one very iron-rich feedstock waste is the so-called red mud that most of you know from aluminum production. And aluminum is made, as you know, from electrolysis, fused salt electrolysis, based on immersing the aluminum oxide into corresponding salt mixtures. and expose that to corresponding electrode processes in which the cations walk to the cathode. But the debris that is left over when you turn the mineral, that means the naturally occurring bauxite, into aluminum oxide, is not like hematite, but it's very impure. You only have 20 to 30% aluminum oxide in it, and all the rest is dumped and called red mud. It's highly alkaline material, and we have globally piled up more than 4 billion tons of that red mud. And yeah, that is poisoning, of course, the nature, as you can see here. And it's, on the other hand, very valuable and rich in metals. So we started to work a lot on this red mud and also other industry waste products. To give you a feeling of these ponds, of a mid-sized pond that you see here, you know, it could easily absorb the Wembley Stadium or the Golden Gate Bridge, or even the great pyramids of Gizeh from Egypt would just, you know, be covered by such a lake. So these quantities are really, really big. And we use this dried red mud, like we use iron oxides, as feedstock for plasma-based, hydrogen-containing plasma-based smelting reduction processes. And that runs in a very similar way, as I've shown before, for the case of iron, where we use hematite, but now with this much higher contaminated oxide material, which contains, as you know, iron oxide, some rest of aluminum oxide, titanium oxide, silicon oxide, and even rare earth metals and so on. So it contains all kinds of materials. And in this recent paper, we could show that in this plasma-based reduction with very lean use of hydrogen, you can turn also this red mud material very efficiently into pure metal and into a neutralized oxide material that you can use in construction. So the use of red mud is, of course, well known in the literature, but this is a very efficient one-step process to turn the entire material into two separate industry materials that can be used. And it's also very, very fast and economically efficient. And we currently start to work together with the aluminum industry to scale that up to larger dimensions. So it has a no-waste strategy also in the sector coupling between iron production and aluminum production and the construction sector. So there's a lot to do in the future, and we are just all, I think, about starting. And just as a little way of summary, I show here on the left-hand side one of these very big direct reduction reactors from Mirex, schematics of how such a pellet shaft reactor looks like. These are the pellets that we saw, and when we could see in this presentation, when we go deeper, you can go deep into the microstructure, go through the phase transformation physics, grain boundaries to gas mass transport. We can do simulations, we can do EBSD and so on. That means for all of us, from the more reactor expert, from the chemical engineering experts, thermodynamic experts, phase transformation, microscopy people, there's a lot of exciting research in for all of us. And we meanwhile even go, as I briefly sketched to you, go down to the even electronic scales, not just in simulation, but also here with differential phase contrast electron microscopy in the experiments. So we really try to understand how the atomistic processes work in this wider field of sustainable metallurgy. So as a conclusion, we try to understand the atomistic foundations of green steel production and also of the sustainable production of other metals, not just steels. And we have many feedstock types and reactions that we in future must take into account, particularly also oxides with higher gangue content. I'm now starting this with two co-workers to look into these effects quite intensely. We work at the moment here mainly on hydrogen-based direct reduction, as I showed you, and on plasma reduction, and I'll show you some of these aspects here with what kind of means and with what kind of mechanisms we are mostly dealing at the moment. And we also, as I showed you, look into other vectors such as ammonia to use that as feedstock for the sustainable steelmaking. And with that, I stop here and thank you very much for your kind attention. Thank you.
Thank you, sir, for your nice, in-depth, full presentation. And now the session is open for discussion. Any participants, if they have any questions, they can ask. Anybody has any questions, so they can raise their hands and I will unmute the participant and he can ask the questions. Yes. Yes, you can ask. You unmute yourself.
Hello, can you hear me?
Yes, yes. Shashank. Yeah. You ask question. Yeah, you are audible. You can ask question.
Hello?
Yeah, you are audible. Yes, you
Okay,
you can ask question.
Okay, my question to Professor Raabe about the usage of ammonia instead of hydrogen. Now, ammonia can lead to a nitrated surface. Can you hear me?
Yes, you can. You can.
Since Professor Raabe, can you ask him?
Yes, I'm not sure whether I could understand the question correctly. If otherwise, please correct me. What I gathered from your contribution is that you're asking whether or what kind of nitride products are formed during ammonia-based direct reduction. Is that correct?
No, I want to ask. Eventually, after reduction, a nitrated layer is going to form on the ore. And that nitride layer may reduce the kinetics of further reduction. So
yeah. So that if I understand the question correctly, you are asking about the role of the nitrides for kinetics of direct reduction.
Right.
Yeah. That's an excellent question. Very good point. So first of all, you are entirely correct that the nitrides form, like the pure iron itself, in part a very dense layer around some of these pellet features. And that, as you correctly allude to, would likewise, like in the case of pure iron, slow down the outbound transport of oxygen. And the diffusion coefficient might be even slower in the different nitride forms than it is in the iron. We must still learn better and understand better which type of nitrides we really encounter. At the very end, like you could see, we have mainly one predominant type of nitride, but during the transient, when the reduction takes place, we form different types of nitrides. So I cannot answer you the question in a quantitative manner, but you are totally correct that also the formation of nitrides is an obstacle that slows down the kinetics of direct reduction. Very good point, yeah.
One more question, a follow-up question. So this nitrogen we have to reduce in subsequent stage making processes. So is it a cost energy intensive process, or cost is not involved much to eliminate nitrogen from subsequent process?
I'm not sure whether I understand your question. You are asking about the costs of the nitride removal, or what is your question? I was not quite sure if I understand it properly.
It's about the cost of nitrogen removal in subsequent process.
Okay, yeah. So the full cost calculation of all of these processes, I'm often asked, but I cannot tell you because I must always repeat that I'm a basic researcher, and the full cost models for that, I think, must be done by experts. No, our first driving force is to at all understand what we are doing before I do a full cost calculation. Our experience, however, so far is that I also was surprised that the removal of the nitrogen from that solid, once you charge it together with scrap, for instance, in an electric arc furnace, is very easy to do due to the vapor pressure of the nitrogen. However, how much of the nitrogen or even nitrides survive in such a melting process and in leather metallurgy, I cannot fully tell because we have to do several follow-up projects and I have to find funding for doing this type of research. The only thing that we could show so far that you can use ammonia to do this type of process, but there's so much in the follow-up on the cost side on the efficiency side and so on that we still have to dive much deeper into. I sometimes, when it comes to the totally correct questions pertaining to cost and so on, I often ask the question back when I look back my 35 years travel in metallurgical research and look even today how much the community publishes in journal articles. I say, why don't you guys ask the same questions to all the other 100,000 papers that are published every year? As a community, we walk nowadays to the world and say all the problems of the world are solved with high entropy alloys and carbon nanotubes or metallic glasses, but nobody ever asks, what is the cost model behind that? So I'm not saying that we do here should not do these cost calculations, but my feeling is sometimes we first must also do the basic science and then work together with experts to do better cost calculations of that. But you know, that was the first paper that we wrote here, so we could not solve all of these questions, unfortunately. And it's very hard to get funding for this type of research, at least in my country.
Well, I think one question we can accommodate. Sambit, you can ask the question. You can unmute yourself and you can ask question. Sambit.
Yeah. Hello, sir. So I'm a PhD student from IIT Ropar. I work in the waste management of steel waste. So my question is like, if we are, what is the better way to recycle the waste? If we go for the smelting purpose or if we go for the solid reduction. So if we go for the solid reduction, we can reduce it and we can extract the iron with the help of magnetic separation. So this will be more economically benefit as compared to if we go for the smelting or for the plasma way, because that will be more consumable of electricity and the power. So what do you think, sir?
Yeah, that is a very, very complex, very big question. It involves very different facets, like, again, the cost models behind the different alternatives, including also the plasma. Then it involves heavily the CO2 and cost footprint of the corresponding electricity, the grid electricity that you use to operate plasma furnaces, of course, at that scale that we need. And third, you touched upon the question, what is the consequence of the different waste products and how do they feed back or serve in sector coupling in the construction sector and so on. So these are all extremely complicated questions. I cannot answer all of these questions. They are much too complicated. But the punchline is that the blast furnace slag is, of course, the established steel factory slag is very valuable feedstock, as we know, for the construction sector. And that is very well established and works. However, that is very different in different countries, because even small impurities that we as engineers know do not really leach out over 100 years and are not harmful are nowadays in certain regulatory spaces in certain countries seen as harmful. That means also in future we will have problems in using the different slags in the construction sector beneath streets and so on as we currently do it. The debris and slag that you get from plasma smelting and from direct reduction are very, very different. Also, when you look into and I want to add that to the pile of problems, when you look into plasma-based reduction, you also get a totally different type of slag formation. So the slag, the protection of the electrodes, the refractories, all of that must still be studied in very, very high detail. Also the question of co-fueling, how you direct the electrode geometry, there's so much to do. So I'm unable to answer all of these questions, but what you correctly put on the radar is that the use of the slag and the sector coupling must be taken, of course, into account when planning future pathways. I think, pertaining to your question, some of the solution might lie in what we call, hybrid methods where you maybe don't take the full reduction out of a direct reduction reactor, but maybe you do it only partially. Then I charge it either in an LD operation or charge it maybe in a plasma smelting reduction furnace with maybe only a very small reductant contribution from hydrogen and so on. So I think, or some of the things can be charged back into a blast furnace and so on. So I think we must look much more into combining the best of the several worlds and be able to integrate it into an operating steel factory. So these are all questions, you know, I wish I had 100 more students, and particularly wish I would have funding for that, because also many industry colleagues are asking me these questions all the time, but studying it takes, you know, a lot of time and care. And so your questions are excellent, but some of them, unfortunately, it's too early for me to answer all of them.
Thank you, sir. Thank you.
Thank you, Professor Raabe, for accepting, first of all, accepting our invitation for this short-term course on green steel. And for your, once again, thank you for your such wonderful, insightful talk for your presentation. Thank you once again. Thanks a lot, sir.
Thank you very much. Have a good meeting. Bye-bye.
Bye-bye, sir. Thank you.